Hi all. Today we'll be discussing the LeetCode problem of the day, maximum product of splitted binary tree. So here you are given a binary tree and you have to split the tree into two parts by removing an edge such that the product of sum of two subtrees should be maximized. And you have to return the product by taking modulo with 10 power 9 plus 7 because the answer will not fit in the integer range. Note that you need to maximize the answer before taking the mod and not after taking it. So first the answer should be maximized, and when you get the answer to that you have to take the mod and return it. So if you look at the examples, so this is your binary tree. So suppose if you split it, if you remove this edge, it splits into two binary trees, two subtrees. This is one and this is the other. So in this configuration, the sum of this subtree is 9 and the left one is 12. So when you multiply, you get much 108. So if you split it in this way, you get the product as 108. But as shown in the example, if you split it in this way, you get the sum as 11 of the first subtree and the second is 10. So here you get the sum as 110, and this is the maximum sum you can achieve. So the output is 110. Now coming to the second example. So here you will get the maximum sum, maximum product when you split it here. So the first subtree is 6, the second subtree sum is 15. So the total product will be 90, and this is the maximum in this example. Now coming to the constraints, the number of nodes in the tree will be in the range from 2 to 5 to 10 per 4. 2 because to have an edge you need at least 2 nodes, and the value of the nodes will be from 1 to 10 per 4. Now let's go over the approach. So to solve this problem, we'll try to find the answer for all possible cases. That means we'll try to remove all the edges. Suppose if you remove this edge, this is one subtree and the rest of the tree is the other subtree, and we'll try to find the answer for this. The same thing we'll do it for all possible edges, and we'll try to find the maximum answer among all of them. So to do it efficiently, here we can see that suppose if you remove this edge, then the tree gets split into two parts. One part is this and the other part is the rest of the tree. So we don't worry about the other part for now. So first part is a subtree which is with the root as 5. Again, if you see here, if you remove this edge, one part of the tree is a subtree with the root at this 3. Similarly, if you remove this edge, then one part of the tree will be again a subtree of the original tree with the root as 4. So from this, what we can see is, if we find sum of all subtrees of this tree, then the total sum minus the sum of the subtree will give you the sum of the rest of the part, and then you can multiply both of them, and that can be your answer. So if you want to take an example, just do a normal post order search on this tree. So first you'll get the left sum, you'll get the right sum, and you'll also add the current root value to it. So by doing that, first you'll arrive at this 8. So when you get the sum as 8, that means you are splitting the edge at here. So the first sum is 8 and the rest sum will be 52 minus 8, which will give you the sum of the rest of the tree. So 8 into 52 minus 8 will give you the first product value, and that you will try to store it somewhere and you'll try to maximize this value. So similarly, once you get for 8 and you also do it for 7. So when you do it for 7, that means you are splitting the edge at this point. So the product will be 7 into 52 minus 7. So once the left and right is done, you will arrive at the top. So your current sum will be left sum plus right sum plus root value, which is 19. So 19 indicates sum of this subtree, and this configuration denotes that you are removing this edge. And if you do 52 minus 19, then you will get the sum of the remaining subtree. And when you multiply, you can get the max value, and you'll try to store this somewhere and maximize this value. Okay, so far we have checked the answer for these three edges. So after this, in the order, you will come to this node. Again, for this, the sum is 9, and the rest of the sum will be 52 minus 9. And this will cover the case for removing this edge. After that, you will arrive at this point. So left sum is 9, right sum is null. So right sum is 0, and the current value is 5. So left plus right plus current will give you 14. So the current subtree sum is 14, and the rest is 52 minus 14. So this will be the configuration of removing this edge. So this is one subtree, and the rest of the tree is the other subtree. Okay, so far these edges are done. Now after this, same goes for 6. So when you get the sum for 6 and the rest of the sum will be 52 minus 6, that will be by meaning we remove this edge. Similarly, we do it for 7, and then we do it for the 3. So when you're at 3, the left sum is 6, right sum is 7, and the current value is 3. So when you add all of them, it is 13. 16. So this 16 indicates sum of this subtree, and 52 minus 16 will indicate sum of the remaining subtree. And this is the case where you are removing this edge. And finally, for the left one also, when you're at 2, the left sum will be this part, which is 19, and the right sum is 14, and the current is 2. So 14 plus 19 plus 2 will be your sum of this subtree. And 52 minus this sum will give you sum of the remaining part. So this is all. This covers the case of removing this edge. So once you finish your post-order traversal, you can see that you covered the case for removing all the edges. So now among all these values, you will just return the maximum value. Now let's quickly code the approach. So first let's find the total sum of the tree. So the total sum and the max, I'll take them as global variables. So let's say total sum and max, and both will be in long. So for finding the total sum, I can just do a DFS on this root, on this tree, and add the sum. Okay, let me quickly fill the DFS function. So you want to find the sum of the tree. So if root is null, then you don't have any tree, so you'll return 0. And then you're currently at 1, which is root, so you'll return root.value. So root.value is 1. So after this 1, you need to find the sum of the left subtree, and you need to find the sum of the right subtree. And to that, you need to add the 1. So by adding all these 3, you will get the sum of the entire tree. So return root.val plus dfs of root.left plus dfs of root.right. So this will give you the sum of the entire tree. Okay, so once you get the total sum, you'll try to first I'll reset the max value to 0. And then I'll call the post order travel. I'll do the post order traversal like we discussed to find the sum of each subtree. And when you have sum of each subtree, you can get the sum of the other subtree by subtracting from the total sum. So let me call the post order and pass the root. So let's name it post order. So again, for the same thing, you'll repeat the same thing here. If your root is null, you'll return 0, and you'll try to find the current sum, current value plus left sum plus right sum. So instead of returning, you'll first store it here. Long sum equal to this. So this indicates sum of a subtree. Suppose you are at 4 and you call this post order with 4. So sum will be root dot value, which is 4, plus here you will have post order. So post order of root dot left will give you 8, and post order of root dot right will give you 7. So currently sum will contain sum of this subtree, which is 19. So if you want sum of the other subtree, you need to just multiply. You need to subtract this from the total sum. So you can have total sum minus sum. So this will give you the sum of the other tree. And this you need to multiply with the sum. And this entire value, you will try to maximize it. So you can write max equal to add dot max comma this product. And at the end, you will again return the sum. Because this post order function is basically doing the same thing as the DFS. It is finding the sum of the subtree. So once you do the post order, your max will be updated with the max product. So at the end, you will return max. But here you have some conditions. You first have to take modulo with 10 power 9 plus 7. So I'll take the mod. And also the return type of the function is in int and max is currently in long. So before returning, I'll typecast it to int. Okay, let me submit. Yeah, and it works. Finally, let's do the time and space complexity analysis. So for the DFS, this is just order of n. N denotes the number of nodes in the tree. And in the post order as well, the complexity will be again order of n, because we are only visiting all the nodes once. Yeah, so these are only the two functions we are calling. So the total time complexity will be order of n. Now coming to the space complexity, even though we are not creating any arrays, but when we do a DFS or the post order, it's a recursion call. So it will take a stack internally. So the complexity, the space it will take up will be again order of n. So time complexity and space complexity both are order of n. I also have the code in Python. If anyone wants to view it, I'll add this in the description as well. And let's catch up in the next video.